Hello, today I'm going to walk you through some of the changes that have to be made to our tree system to accommodate language P with its quantifiers and predicates. And thankfully, this is really pretty minimal. So just for a useful bit of a recap or a redux, trees, semantic trees, check for consistency. And so remember that an open tree, which is a tree that has at least one completed open branch, indicates a consistent set. Okay, while a closed tree, that is one with every branch closed, indicates an inconsistent set. Right? And finally, a branch of a tree closes whenever some sentence and its negation are present on the same branch. And so effectively what we're saying here is that any situation, and a tree is designed to look at every possible situation, any situation that's impossible gets closed off. And if all situations are impossible, then of course you have an inconsistent set in front of you. And so remember, the way to set this up, this is again just information from the text itself, but remember that some sentence is a tautology if the tree for the negation of that sentence closes, and some sentence is a contradiction if the tree for that sentence closes. Two sentences are equivalent if the tree for the negation of the biconditional connecting those two sentences closes, and any given set of sentences, if it entails some further sentence, then the tree for that set plus the negation of the thing entailed should close, right? So that's again just a brief redux on some of those properties. Again, you can review the earlier chapter in which trees are covered if you're a little bit fuzzy in that, and review your notes. That may be necessary at this point. But again, trees are going to work almost exactly the same as usual. We're not going to really change anything about the way they work. We're just going to add a couple of rules for our quantifiers, and that's really all that we'll need. And so again, these are the rules, right, by which the trees operate. These you should be, again, if you're not, you should either be familiar or get re-familiar with all of these rules, those that branch and those that don't. Recall the rules for conjunctions. A conjunction does not branch because if P and Q is true, then it's going to be true that P is true and Q is true, right? So this doesn't give us any alternate possibilities here. There's not more than one way for that sentence to be true. But a negated conjunction, right, there's more than one sentence for a negated conjunction to be true, and that's either if one conjunct is false or the other conjunct is false. Right, and so similarly, again, through this is actually just a clip straight out of the textbook. So go ahead and review that if you are a little bit fuzzy, don't remember it as well. But again, the first step to doing trees in P is to refamiliarize yourself with the way that trees work in S, because again, there's only a very minor couple of changes we're going to add. So one of those two changes is that we have a new rule, new branching rule, for decomposing the existential quantifier. And it's I say branching. It's not a branching. It won't actually branch, but it is a rule for decomposing things in a tree. So when you have an existential quantifier, right? What you do is you use, this is called existential instantiation is the technical term for this. You don't have to know that term. You just have to know how to do it. The way that works is that when you have an existential statement, such as you see here, E of x, px, right, which is there exists an x such that x is a p, right, whatever that predicate is. The way that you handle that on a tree is that you cross it off and put some constant, right, instead of a variable like x or y or z, you'll put some constant individual. And the thought process behind this is that we say, okay, we know that there exists something that is a p. So you might do something like that. There exists a plumber. Call him Albert, right? I mean, so that's effectively what's going on here. Is we're saying, let's just come up with a name for some arbitrary plumber that we're going to say exists. There's a restriction on this. The idea is that whatever constant you use, whether it be A, B, C, D, whatever, or P or Q, whatever constant you use to instantiate this existential claim cannot occur previously anywhere in the tree. Okay, because the idea is this: if we've already talked about Albert, Albert's a good swimmer, like, as a previous sentence on this tree, and Albert is, a mammal, and Albert is whatever, right? If we have already said things about Albert and we say there exists a plumber, we don't want to say that Albert is that plumber. We don't know that. Okay, so the idea is that we're having to pick some sort of arbitrary sort of label to say, okay, you know, there exists a plumber. Let's just pick arbitrarily some constant. Say that's the plumber, right? We're just you just give a name to this thing that exists. That's all we're doing here. We don't want to assume that this particular thing also, you know, we don't want to add information that isn't actually there, right? If somebody says Albert is a great swimmer and there exists some plumber, we don't want to just assume that Albert is the plumber that we're talking about. That would not be valid. But if we, you know, say, you know, Albert is a great swimmer, then we can say, you know, Biff is the plumber that we're talking about. At least, you know, it's still possible that Albert is the plumber, but we just don't want to assume that. And so that's why we use any constant that doesn't previously occur on the tree, and then of course you cross off that existential quantifier once you're done. You only do this one time. This existential quantifier means at least one. Okay, so we're going to put one in there, right? And that's how that's going to go on a tree. The tree system, as you'll see once you get practice doing a number of these, is constructed in such a way that it will generate for you a world just large enough to test the consistency of the set of statements that you put into it. Right, and so if there's you know, lots of different existential quantifiers, you're going to end up with lots of different you know, possible constants that go in here, but only enough that you can just test to see whether the system is consistent. It's very elegant once you start looking at over some examples and thinking of it from that level of abstraction. But really, the thing you need to know how to do is when you see an existential on a tree, you just instantiate it. You replace the x, right, in the sentence that's being quantified over with some constant, right? And then as long as that constant doesn't occur previously in the tree, that's the rule. All right, so we also have to add a rule for universal quantifiers. And the way to decompose those is what's known as universal instantiation, right? But again, you don't have to know that name. You just have to know the process, how to do it. And so say we have somewhere on our tree the sentence for all of x, p of x, right? That means, you know, for all of x, x is a p, right? So that means everything is a p, essentially. And what you do is to instantiate that, you put in a constant, right? A and B and C or D or whatever, and you instantiate it for every individual that is on the tree somewhere. Okay, so if there's an A on the tree somewhere and a B on the tree somewhere, you'll want to substitute A in for the X, and you'll want to substitute B in for the X, and then you're done. All right, you're not done instantiating a universal claim until all right of the universal all of the constants have been instantiated once for every universal on the tree. Okay, and also you don't ever cross them off, right? Because when we say that everything is a P, we mean that A is a P, B is a P, C is a P, D is a P. We're never just done, okay? And so those never get crossed off. You just sort of keep adding, you just keep instantiating them until you've got one for every one that's actually on the tree, right? So that's the process for the universal. We don't generally deal with negated quantifiers, so we don't need really special rules for them. Basically, what we do when we come across a negated quantifier is just replace it with its equivalent form. So you remember that not universal not is equivalent to existential, and not existential not is equivalent to universal, right? And so basically, all we do is swap it out. And so if you have a negated, if you say it is not the case that for all of x, p of x, you just swap it out. You swap out the universal for not existential not, and then drop those double negatives off the beginning, and then you end up with there exists an x such that it is not the case that p is an x, right? Notice those say the same thing. So saying that not everything is a p is the same thing as saying there's something that isn't a p. Okay. Likewise, with a negated existential, you just swap out the, not universal not, drop the double negation off the beginning, and then you end up with for all of x, it is not the case that x is a p. Right. So again, that says the same thing. It is not the case that there exists something that is a p, means nothing is a p. And if you want to say for all of x, x is not a p, right? That's another way of saying nothing is a p. So basically, again, we're just going to swap out one thing for its equivalent if we end up looking at a negated universal or a negated existential. So we don't really have to deal with those things other than simply swapping them out. All right. So let's take a look at least one example here. This example is the first one from the Chapter 14 exercises, and we can sort of do more of those later in some format or another. But for the case, here's the first one. Okay, and so basically we have this set down here that consists of two sentences. One, the sentence that for all of x, x is a p, or for all of y, there exists a y such that y is a q. And then the other sentence is there exists an x such that x is a p and q and b is a q, right? That's the idea. Now technically we don't have to have that qb in the scope of the quantifier, but it doesn't hurt if it is. Okay, so let's set this up. Again, we just put each sentence on its own line of the tree. Okay, so you have broken them out that way. And what I want to point out is this. Okay, so again, you have to pay attention to what the main connective or operator of each of these sentences is. And so here in this sentence, the main connective or operator here is this is a disjunction. So it's a disjunction. This disjunct here is a universally quantified claim. This disjunct is an existentially quantified claim, but this is the only thing that we have to deal with right now. On the other hand, the second sentence here, this is an existentially quantified sentence. This thing is the operator that has the whole statement in its scope. Okay, and so we have our choice. We can deal with this one here first, this first one, or we can deal with this second one. But of course, this one, notice, this one will branch. If you'll let me sort of write with the mouse there. Hey, great handwriting. Okay, and the second one will not, of course, that will not branch, right? And so that's always the best one to start with. Here's another thing. In general, you want to always decompose your existential claims before your universal ones. Again, the system will still work if you do it the other way. It's just that it's going to be a lot more complicated and take a lot more time and paper if you do it that way. And so again, the reason you want to do the existential first is because you have to introduce a new constant for that. And so if you've already done a universal and then you introduce a new constant, you have to go back to the universal and do this, do the universal over again for the constant that you just introduced. So again, existential before universal is a good rule of thumb, and non-branching before branching is another good rule of thumb. Again, the system works even if you don't do that, but you should do that. All right, so the first thing we're going to do is we're going to do this sentence here. There exists an x such that x is a p and b is a q, right? So notice this b here is a constant. It's an individual. Okay, it's not one of these things that's being quantified over. The x is the thing that's being quantified over. So what we're going to do is we're going to eliminate this existential here. We're going to instantiate it by putting in a constant in place of x that doesn't exist anywhere else on the tree. And so for those purposes, may as well select a, for example. And so what we've done here is we have substituted the a in where the x was in the sentence that was quantified over. And then we've, because this wasn't quantified over, we just sort of kept it. And so now we have the sentence PA and QB, right? That's, and then we can cross this one off because, it's done, right? We've instantiated it. Okay, so now again we have a choice of two different lines to decompose. We have this one here, of course, that branches, and we have this one here that does not branch. And so again, you want to choose things that don't branch over things that do. So let's go ahead and decompose this sentence here, and we'll just use the ordinary rule for conjunctions. Nothing special there. And so we decompose that into PA and QB and just cross this one off because it's done. Now we have that first line, right? This sentence up here to break down, and this one, in fact, is going to branch. So I'm going to shrink things down and then branch it up. And so it's going to branch into the first disjunct and the second disjunct because what was between them was a disjunction symbol. Okay, so we have now two branches of this particular tree. We have one with a universal on it, and we have one with an existential on it. And we have to do them both before we're all done here. But again, existentials before universals so that you can introduce as few things as necessary. So remember, with an existential claim, what you want to do is you want to instantiate the thing being quantified, in this case the y. You want to replace the y with something that does not already occur on the tree. And so if we're going to just go alphabetically, that would be something like C. So we want to replace this y in the sentence quantified over with a C. and then cross off the existentially quantified sentence. So we cross that off, we put Q, C, okay, because C doesn't occur anywhere else on the branch. We're saying something's a Q, let's call that thing C, right? And of course, now all we're left with is this universal over here. And remember the rule for universals, you have to instantiate it, you have to replace that X, in other words, for everything that's already on the tree. So we see there's an A here, there's a B here, right? There's A's, B's, etc. Right? X's or Y's are variables. You don't have to count them. And then we've got this C here. It's another individual. And so what we're going to have to do is we're going to have to do this once for A, we're going to have to do it once for B, and we're going to have to do it once for C, and then we're done with that universal. But remember, we don't ever cross off the universal. So here you see that's done. We have, PA, PB, and PC. And so now essentially the tree is completed, right? So even though this sentence here doesn't get crossed off, we know it's completed because in its branch, it's been instantiated for every constant on the tree, for A, for B, and for C. And so now we get to take a look. So if you're tracing up through this branch, you'll see that we don't have a sentence and that sentence's negation, okay? And so this branch is going to end up being open. This branch, we do not have a negation and, a sentence and its negation on the branch. So no problem there. This branch is also going to remain open, which indicates that the set that we gave you initially was in fact consistent. Right, so there it is. There's a completed tree done in language P.